Slot embedded conductor skin effect. This is a stator slot of a large induction motor. The induction motor operates at AC current with a frequency of 50 Hz. The slot is made of ferromagnetic material with the relative magnetic permeability of 1000. Our task is to find the current density distribution, effective resistance, and the Joule losses in the conductor. And we should compare two designs with solid conductor and a conductor subdivided in two parts. The conductor dimensions are 8 by 60 millimeters. The total current in the slot is 600 amperes. Let's start QuickField now. In QuickField I create new problem. Slot. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is plane parallel. Length units are millimeters, and the model axial length is 1000 millimeters, 1 meter. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The geometry model is simple, so I will draw it here. Insert shape, rectangle, anchor point is here. The conductor width is 8 millimeters and the conductor height is 60 millimeters. Insert. Next I will insert the slot, another rectangle with 13 millimeters and the height is 100 millimeters. Insert. Close, zoom to fit, and we should insert the insulation layer. Again, rectangle, 10 millimeters by 61 millimeters. Insert. Close. Here you can recognize the conductor, the insulation, the ferromagnetic part, and the air outside. QuickField cannot simulate magnetic field distribution in the infinitely large space, so we need to restrict the simulation domain. Zoom out, switch to insert mode, change the line type to be the half arc, and draw the air block boundary here and here. Now let's assign labels. For labels we will provide material properties. Switch to select objects mode, click the object to select and type in the label name here. This is air. Click here. This is steel. Zoom in. Switch the zooming mode off. Click here. This is conductor. Again I need to zoom in. This is the insulation. Zoom to fit. That is all for block labels, but we should also assign labels to the external boundary. Select objects mode, click to select, hold the Ctrl button pressed to select multiple objects at the same time, and assign label external. Okay, now let's provide physical properties for these labels. Double click the label name in the tree. For the air, magnetic permeability is 1. Okay. For the insulation, magnetic permeability is 1. For the steel, magnetic permeability is 1000. The steel is laminated, so I do not specify electrical conductivity. Okay. And for the conductor, which is made of copper, relative magnetic permeability is 1, electrical conductivity 57 megasiemens per meter, and the total current in the slot is 600 amperes. This is the peak value. Okay. Far away from the slot the magnetic field fades to 0, so at the external boundary I specify 0 magnetic potential. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button, save all problem files, and run the analysis. Problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines and the color map of the current density distribution in the slot. As you can see, the current density distribution is not uniform. That is caused by the eddy currents. I'm going to use the contour tool, the line type to be the straight line. Click and drag to draw the contour here. And now I will get the current density distribution along this contour on the XY plot. On the left is the bottom of the slot, and on the right is the top of the conductor. You can choose the values to display here, and you can see exact values in the table. The coordinates, current density, and other parameters. You can also use contours to calculate integrals. Close, close, contour clear. Now I will click inside the conductor. Follow to the integrals. Here I can calculate total current, which is 600 amperes as I have specified. I can calculate joule heat average value per 1 meter of conductor length. Peak value. Using peak value of the joule heat and the peak value of the current, I can calculate the resistance. The current value is 600 amperes. The joule heat losses peak value is 61.386 watts. Then the AC resistance is joule losses divided by the current squared. This is the resistance per 1 meter of the conductor length. The resistance value depends on the frequency, that is why it is called AC resistance. And if I change the frequency to 10 Hz, run the analysis again, zoom in, use the contour tool, click inside the conductor, integrals, total current is the same, but the joule heat value, peak value is 26 watts. So at 50 Hz it was 61 watt, and at 10 Hz it is 26 watts. And the resistance will be much lower value. Another way to reduce the eddy currents is to subdivide the conductors. Open the geometry model, zoom in, switch to insert mode, change the line type to be the straight line, click and draw the straight line here in the middle. Now I have two conductors. Switch to select objects mode, click to select. This is conductor 1 and this is conductor 2. In conductor 1, which is made of copper, the total current is 300 amperes peak value, and in the conductor 2, which is made of copper, the total current again is 300 amperes. Okay. Now let's build the finite element mesh. Change the frequency back to 50 Hz. Save all problem files and run the analysis. Let's take a look at the results. Let's zoom in. As you can see, the current density distribution has changed. Again, I will use the contour tool to draw the contour line here in the middle along the vertical axis. open the XY plot, and here is the current density distribution. And if I copy this picture and paste it here, you may see the difference. On the left was the current density distribution in the solid single conductor, and here is the current density distribution in the subdivided conductor. And what about the integrals? Close, contour clear, click to select the conductor, click to select another conductor, integrals, total current, the same 600 amperes, joule heat losses, again use Excel. Now it is 2 conductors, 50 Hz, 600 amperes total, and the peak value of the joule heat losses is 103.65. Then the resistance is 0.28 milliohms. It was 0.17 when there was only one conductor. There are much more you can do in the QuickField post-processor to analyze the results. Contour clear. I can use the local values to click any point and get the exact value of the flux density, current density, and other parameters. And you can edit the point coordinates here. You can also adjust the field picture and switch on, for example, the magnetic flux density. You can change the presentation type between root mean square values, peak values, and the momentary values. For the momentary values, you can change the phase and see how the magnetic fields varies in time. If you search for the slot embedded conductor skin effect on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resultant pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.